Hi, in this video we're going to talk about something called shunting inhibition. And shunting inhibition is a phenomenon that hasn't necessarily been implicated in learning and memory, but it definitely is an important neuronal circuit interaction to understand, and experts are looking for it in something called gain control, which may prove to be pretty important. So we're just going to focus on it briefly here. And shunting inhibition is a phenomenon that's separable from the regular form of inhibition you've probably already heard about in your first neuroscience textbook. That first form of inhibition really offers linear differences in voltage change due to inhibitory synapses, and it really it's rooted in the linear spatial and temporal summation of inhibitory postsynaptic potentials. Those are IP, SPs, and I should have drawn those in red. So here, inhibitory postsynaptic potentials and excitatory postsynaptic potentials here in green. And that first form of inhibition has to do with linear and temporal summation of EPSPs and IPSPs. And just a brief overview of what that means is to show what that means. I have a little drawing here where we have one excitatory synapse and one inhibitory synapse. The excitatory synapse has sodium channels embedded in the postsynaptic membrane, and the inhibitory synapse has chlorine channels embedded in the postsynaptic membrane. And both of the electrochemical gradients of these ions would dictate that they would flow into the cell if the channels were to open. The sodium would depolarize the cell and the chlorine would hyperpolarize the cell. And we see we've given this postsynaptic membrane a negative 65 millivolt resting potential. And just to give you an idea of what this first form of inhibition is that we're trying to isolate away from shunting inhibition in this video, is we could say that if these sodium channels were to open, if this presynaptic neuron were to fire, then some positive current would flow into the cell and try and passively move its way along, and this Cl minus channel, this chlorine channel, would also open. Say the inhibitory channel would flow, and some negative, should be in red, negative current would come in, and essentially they would flow and hit each other at this point. And it's good to keep in mind that really current flows in both directions, and what would happen is in this region the voltage changes would summate with one another. So the final voltage change would be a summation of the two that comes from the two channels, and that's the way spatial temporal linear inhibition works. And with shunting inhibition, though, we're talking about a sort of separable phenomenon. We don't get linear changes in voltage, we get divisive differences. Really, it's by the difference in voltage change comes from dividing the original voltage change by some factor. And to really isolate that phenomenon, we're just going to forget about this inhibitory synapse for just a moment, and for argument's sake say that the reversal potential of this inhibitory synapse is also negative 65 millivolts. And if you see, I've made the reversal potential of these channels the same as the resting potential of the postsynaptic membrane. And I did that for a reason, is to isolate this shunting inhibition from a phenomenon from that other form we just drew a moment ago. And just a quick refresher of what a reversal potential is. A reversal potential is the voltage at which no net flow of ions occurs through a channel. So the same amount of chlorine will flow in and out of the cell. So there will be no net change in really charge due to this channel opening. That's the definition of a reversal potential. So since we're at negative 65 millivolts here, that's what would be the case if we were to open these channels. So now we pose the question, if this presynaptic neuron were to fire, this red neuron here were to fire, and these channels were to open, am I inhibiting this postsynaptic cell in any way? And the answer is yes, we are inhibiting it. Now, are we hyperpolarizing it? Not necessarily. That's the definition of a reversal potential. So if these channels were to open, we wouldn't hyperpolarize the cell, but we would still be inhibiting the cell. And the conceptual way to understand this, it's a bit of a hand-wavy way of describing it, is to say that these channels that are opening up, although they're not hyperpolarizing the cell directly, are offering a shunt or a leak for current to flow in and out of in case some other excitatory postsynaptic potential happens immediately after these channels open. So imagine that these red channels are consistently and continuously open, are activated. The presynaptic neuron is in tetanus and it's continuously firing. Then if some excitatory synapse were to fire in its close local region, then we'd offer a shunt for that current to leave from. Now, that's the conceptual way to look at it, but the real mathematical way to look at it comes from really just a quick analysis of Ohm's law. And Ohm's law says that V equals IR, or the change in voltage equals the current times the resistance. And in this case, we're talking about input resistance. That's input resistance. Now, that's a resistance separable from the internal resistance to flow. So one form of resistance we've learned about in neuroscience is this internal resistance to passive flow, where a current may be traveling through the cell, and really this current experiences resistance to flow due to maybe the diameter of the tube or the resistivity of this dendrite. But that's not what we're talking about when we say input resistance. Input resistance has to do with the number of channels or conductances open. It's how hard it is for an ion to go through a membrane. So it's really the resistance that an ion experiences as it travels through a membrane, through these channels. And the question is, when I open these chlorine channels, what am I doing to that input resistance in this Ohm's law equation? Are we increasing this input resistance, or are we decreasing this input resistance? And if we're opening more channels, we're actually decreasing input resistance because we're offering more paths of conductance for these ions to flow through. That being the case, if we write some inhibited form of this equation, once the channels are open, we say the new change in voltage, delta V prime, is equal to the current times R input prime. This is after the chlorine channels have opened. Let me just fix the spelling here. This is after the chlorine channels have opened. Then this new R input would be smaller, and the delta V prime that would come about would be only a small fraction of the original delta V, of this blue delta V here. And the real reason behind it is that this I is supplied by some excitatory postsynaptic potential that occurs immediately after this red channel is open. So we have the same current supplied, and we just have a different excitability, a different input resistance in the local region of space, of this inhibitory neuron. So it literally acts as a shunt. It makes the local region less excitable than it was a moment before. And now a good question to ask yourself about shunting inhibition is, if the reversal potential were not the same as the resting membrane potential, would we still see this phenomenon? So if, for example, we had a resting potential of negative 60 millivolts this time, and we open this channel now, would we still have this shunting inhibition phenomenon at play? And the real answer is yes. We'd have both types of inhibition at play. So the second we open these channels, these chlorine channels in this case, the reversal the chlorine would flow into the cell, trying to drive this resting potential, this membrane potential, towards the reversal potential of chlorine. Remember, the final potential is derived from the Goldman equilibrium. It's just really when you combine all the Nernst equations of each conductance in the membrane. So each individual channel will try and drive the potential towards its reversal potential, towards the channel's reversal potential. So we would have that first form of inhibition where we have an IPSP, an inhibitory postsynaptic potential, come in, but we would also have this shunting inhibition phenomenon at play. The input resistance of the local region would still be decreased by opening these channels. So we'd really have shunting inhibition at play, just clouded maybe by that first form of inhibition we talked about. And one last little question to think about maybe on your own is, if I opened up a positive channel, if this were an excitatory channel that I opened, maybe a sodium channel, would I still be inhibiting? Would I still have this shunting inhibition phenomenon at play at the local region of membrane space? And that's a good question to think about on your own. It's a bit odd because we're talking about a positive channel, an excitatory channel offering shunting inhibition. It's a good question to ponder, and we might get to it in another video. But for now, I thank you for listening and hope to catch you in the next video.